Good morning, everyone. I'm very pleased to be here to present this project. It's very personal to me, but it's not just me. It's a whole bunch of people. It's been a collaboration between ESA and some other people from a startup company called Part3. So what is it about? We're on Mars is an online interactive map of the ESA ExoMars 2018 rover candidate landing sites. That's been thought and designed for the general public. So the project started about a year ago with an initial idea, and it's been done as an ESAC training project. So ESAC is the ESA establishment in Madrid. And as I said, it's been done in collaboration with CartoDB, and those people are based in Madrid and in New York. So CartoDB is an online platform to easily visualize and analyze data on a map. This is an overview of the type of visualization you can do with CartoDB. It's extremely powerful, and this is what we've used, among other things, for this project. So the project, the objective and the original idea for this project was twofold. It was technological and educational. By the way, I have pretty much no experience in outreach or education. It goes as far as taking my family to Space Museum, that's it. But I'm a planetary data engineer. So technical objective was to experiment the use of modern open source web mapping technology applied to planetary science data and geospatial information, and educational, because based on my experience of working on Mars Express mission and ExoMars 16 at the time, I thought it would be a great idea to use this to increase the public awareness of the ExoMars mission. It's a very exciting mission, and generally, more generally, the scientific and robotic exploration of Mars in Europe. So, just a word about the ExoMars 2018 mission. ExoMars is a program in two parts. You have the 16 mission and the 18 mission. The 18 mission is going to land a rover, and the main goal of the rover is to search for signs of life, either past or present. So, yeah, it's going to be our first rover, so it's quite exciting for us in Europe. And so where are we going to land? So that's the question that's going to take years to answer. And the process has started already 2 years ago. So a working group of experts has been appointed by ESA and the European, by ESA and the Russian agency, because it's a joint collaboration between the two agencies. In December, there was a first call to the scientific community for proposing landing sites. 8 were proposed, and then they were discussed in a first workshop in Madrid in March 2014. At that moment, 4 landing sites were shortlisted, they were shortlisted for further investigation, both in terms of scientific interest and engineering safety. So those are the names of those 4 landing sites: Mars Vallis, Socia Planum, Aram Dorsum, and Ipanis Vallis. Then followed another workshop to discuss about those landing sites. And now we are very near to the next workshop and next event, which is very important, because it's there they're going to decide, they're going to select 2 of those 4 landing sites. One of which is going to be the main landing site, and the other is going to be the backup landing site. And from there, scientists who have been working on characterizing those landing sites will have 2 years to characterize them and investigate them even further. And 1 year before launch, ESA is going to make the final decision based on this working group recommendation. So the interactive map itself, it's been designed to guide you, or guide the public who doesn't have much knowledge about Mars mission or planetary science, through the main scientific engineering constraints for the landing site, selection of these landing sites. and it allows you to explore Mars and each candidate landing sites using a selection of the same ESA and NASA imagery data that are being used by the scientists to actually characterize and study those landing sites. When I say a landing site selection, it's very important because we can put more data, and at the moment it's we can put more data. So it relies on CartoDB and more generally on open source mapping technology, so for processing the data, storing and visualizing all the data on the web. So you can have access to this map from that URL, wellmars.co, and I thought it would be better to just put a few slides rather than trying to make a demo. It's always risky to make a demo. So if you go to the website, this is going to be the landing page. You can immediately launch the map, or if you want to know more, which is pretty much what I'm covering now, you have further information and acknowledgement of all the people that have been involved in that project. So if you click on that button, you will end up on that interface. So as I said, it's been designed so that it guides you throughout this story of which type of constraints scientists and engineers need to comply to select the landing sites. So just to give you an idea of the interface, you have it's typical map interface with the typical controls and a scale bar. Very important, the scale bar. What you have in addition is this navigation control at the bottom, which allows you to go to the next slide, and that kind of help you to follow the story. You can also click on each of the individual landing sites and jump directly on each individual landing sites. So I'm just going to go through them quickly. Here you see the elevation constraints. So you see the dimmed part of the map here shows the elevation higher than -2 kilometers, which is a requirement for the entry vehicle to slow down in the atmosphere. Then, because the rover is solar powered, you need to be landing in an area on Mars where it's going to get enough sun for it to operate. Then it shows the geological constraints in terms of age. The scientists are after really old material on the planet. So here again, you see the latitude constraints, but you also see in the dark areas all the areas that have been ruled out for the selection of the landing sites. All right, then you move to each of the landing sites, and on the top left you have a description of the landing site, why it's been selected. Here you see the landing ellipse. If you mouse over the ellipse, you're going to see some kind of tooltip explaining why it has this shape and why it has this uncertainty. On this base map, you can see an HRC mosaic, and those strips are the NASA high-resolution imagery that you can zoom in. So I took a few screenshots of this is the next site, Oxaplanum. If I zoom in, you can see details higher than, with the resolution higher than 1 meter per pixel. This is, for example, half a kilometer. Then Ipanis Vallis, and another snapshot of Ipanis Vallis in a close-up. Another one. Dorsum, and finally, okay, another snapshot. You have pretty great details thanks to the high-rise imagery. And okay, finally you have the what's next. So in 1 month, here we explain that in 1 month we're gonna, or ESA is gonna select 2 of those 4 candidate landing sites for further study, and encourage the people to follow up on the Twitter account that we've set up for the project. because obviously we're gonna try to catch up with the news of the mission. So most importantly, this project has been done as it was a training project, as I said. So it was something done in parallel of my work, and although we had an amazing support from the CartoDB team, from the beginning we decided that the project would be open source, and we want the project to grow, and we want it to keep open source and to be collaborative. We have many more ideas, and we think that educating through maps is really great. And we've been doing also this in collaboration with other more scientists, people from this working group, people at UCL. So hopefully the landing sites they've been working on are going to be selected, and we're going to be able to enrich this map interface with more data, maybe more annotation. And what we want is to get feedback from the community, from the public. And we encourage people to share the tool and to follow us on Twitter. So the project doesn't stop there, and so wherever you are, if you're an average education professional, a journalist, planetary scientist, or web developer, you can help. All the source code is open source, as I said, is on GitHub. If you're familiar with GitHub, you can reuse it for your own purpose. You can adapt it to whatever you want to do. If ISA is interested in reusing it for the purpose of outreach for ExoMars, we are really happy. We will be happy to keep collaborating, and that's it. Thank you very much for your attention.
Okay, thank you.
Any
Questions? Well, I have one. Will you involve ExoMars 2016 to make images, new images of the potential landing site?
No, I don't think this is foreseen, because it's not a surface mission. 16 is a mission to observe the atmosphere, so there is a camera, but it's we will rely on high-rise NASA missions for that.
And just, I mean, one thing which comes to mind, I mean, there are several meteorology, climate projects related to Mars which are being developed, and I think a nice addition would be to look at the meteorology and the climate, you know, on both sides, and to connect the surface with atmosphere. That would be an idea.
Yeah, but this is something that is already studied. Obviously, okay. You know, the winds.
Yes.
It's something that you have scientists, atmosphere scientists working on that. Something considered, obviously.
Yes.
You know if anyone's using it next week as part of World Space Week, because the theme is Mars. Do you know if anybody is?
I don't know about Space Week next week. Every
year.
Every year.
If anybody will use it.
Space. Well, I'll try to get people to use it because the theme is Mars. So.
Anybody can use it. Anybody can use it, and anybody can download the code and make it his own and adapt it for whatever purpose. So you can just take it as it is. If you want to talk about the ExoMars mission.
Okay, thank you again. So let's move on to the next speaker, the paper by Planetary et al., given by Machado, involving the public and students in planetary science.
Hi, my name is Pedro Machado. I will give this class in the behalf of João Retré. Let me start by presenting the Institute. The Institute of Astrophysics and Space Science is the biggest national research infrastructure in this area and is hosted in Lisbon by the Astronomical Observatory of Lisbon and in Porto by the Porto Planetarium. So, as you see here. IA has been doing research in planetary science for a long time, and some examples of this research include exoplanets, solar system dynamics, planetary atmospheres, and the study of small bodies of the solar system. Currently, our work is mainly focused in planetary sciences in the detection and characterization of atmospheres of exoplanets, and also in the study of the atmospheres of planets in the solar system, as mainly Venus, and now also Saturn and Jupiter. So this is just some highlights of the work we are doing now. In parallel with scientific work that is done in this area, we are committed to bring planetary sciences to students and general public. Our strategy, as you can see, is direct involvement of schools, public lectures, public planetary events, social and media presence, and both between outreach and sciences. One of our main objectives is to take science to schools, and as is exemplified by the project Astronomy is for Me, aims to involve directly secondary school teachers and students in the learning of astronomy through hands-on protocols that require the use of telescopes. One example is the determination of Jupiter's mass through the observation of its 4 largest moons. Students conduct their own observations, acquiring the images they need with the help of small telescopes. Then they perform the necessary measurements in order to get the mass of the planet using Newton's law of universal gravitation. Besides the fact that they are extremely enthusiastic with this project, this gives them the opportunity to build skills on some data reduction, image analysis and computing. And so far they have produced quite impressive results with an error in the calculation of Jupiter's mass of only 1.5%. We also have projects for younger students where they learn some basic concepts about the solar system, for example, the influence of the moon and the sun on the tides and scales in the solar system. In March this year, IA was at the Malta Science Expo 2015 with the workshop Our Wonderful Solar System, and several hundreds of press school children attended the workshop where they could learn and see the scales in our solar system. This was done making use of a solar system model contained in the Universe in a Box kit from the Universe Awareness Project. For the public, one of the ways we have of involving them is through, for example, our biggest monthly activity called Nights at the Observatory, will be this week, that has an average attendance of 150 people per session. In these interactive lectures, they are given by IA researchers and myself. We provide information about several topics of astronomy, including planetary sciences. And it's very beautiful, our national observatory, as you can see. We don't conduct these public lectures only in our spaces, but we also go to schools as well, or wherever they are required. One good example of this is the College School Bankian Planetary, where we have conducted already several lectures about the topic of planetary sciences with an attendance of several hundred people. For instance, the Rosetta things, we are always there with a lot of people in schools and so on. Another way of reaching the public is through special planetary events like moon or solar eclipses, transits, asteroid flybys, etc. In these events we can get an average attendance of 2,000 people per session. This was the case of the supermoon in 2013 in the session depicted in the image. It was a bit too much. These kind of events have a strong media coverage whenever the planetary events take place or an article of scientific nature is published and gets the attention of the media. We provide them clarification. Besides this, we keep the public and the media informed through the webpage and social networks that reach in Portugal over 500,000 people. Finally, science and outreach have created, in some cases, a real bond. With outreach participation actively in some of the sciences that is done. One example of this was the Venus Twilight experiment during the transit of Venus in 2012, and an expedition, worldwide expedition organized by the Observatory of Paris and Nice to observe the last Venus transit in 2012, as I said, and there were 9 teams in this expedition, and we formed one of the teams. Both part science and outreach quickly realized that joining efforts would result in some major technological advancement in observational techniques, like the example of the outstanding all-terrain elephantorial mount that you can see there. So this image was in the NASA webpage. Was an idea from communication to sell our Twilight experiment, and it really worked. Another example is the recent creation of a stellar occultation group. The activities of this group started the last year, but we already have a very strong involvement of the academic community, which in turn is strongly involved with the outreach. So it's really attracting people, getting more and more people near our group. Well, some conclusions. Growing activity for students and professors with ongoing and underway projects which aims the involvement schools through lectures and hands-on projects that required use of small telescopes. Strong involvement of the public through the organization of several outreach activities where professional researchers give lectures with an average attendance up to 2,000 people per session, and the collaboration between science and outreach in order to create strong and diversified outreach activities. And thank you very much.
Okay, thank you. Questions? Yes, Karen.
Have the activities that you do changed over years as you take on feedback that you get from people?
Oh yes, definitely, definitely. And it's growing in the last few years. It's totally different from 10 years ago. So it's, I was not when you said that in your talk, and it's quite a major difference now. And with this bigger European missions as the Rosetta mission, that makes really the difference.
Another question? Well, I want myself. I mean, you are in Portugal, the science office is in Portugal. Are you going to establish, or do you have some established link, collaboration with the Europlanet Outreach Science Office?
Jean has some contacts, but I think that we must improve that. Really.
Yeah. We'll talk to. Okay.
We will, and thanks for that.
Thank you very much. So congratulations again. So we move to the last talk by San Martin and Blanco. This talk is given by Professor Juan San Martin. Outreach testing of ancient astronomy.
Sorry, let me start by saying that being 74 years old, the subject fits me well. Also, that being 74 years old, I feel more at ease in this session with all the mix-up for you, which hopefully I'm not responsible for. Well, this work came out as an outreach, I should say educational, nothing in the social outreach sense, but it's outreaching. It came out from a presentation of the rector or chancellor of president of Universidad Politécnica de Madrid in the Royal Academy of Engineering of Spain, which is, we find that there is a decreasing interest in natural science in too many students as compared with how they are very interested in hardware and software and whatever, digital devices applications. And the approach rests on two features. First, empowering, very modern word, of teenage students to understand some regular natural events around. There's very few educated, in the English sense, people they meet could do. Secondly, understanding that rests on personal capability to test and verify experimental results from the old science astronomy with simple instruments going down to the Renaissance and so on. Astronomy, all astronomy basically involved observing and registering values of angles along with times, either on the ground or in space from the ground. I mean in the old times, not now. On the ground measurements are particularly simple. The gnomon, a simple stick planted vertically in the ground, allow understanding solar motions, even lunar motions, I'll say later, is observed from Earth, as opposed to the heliocentric picture above, which is very helpful to understand it much better than the geocentric picture, but they measure things on the ground. It allows determining the latitude of the point of observation, at about 40 degrees, 0.4 degrees, 4 degrees, 40.4 degrees. And also the ecliptic, the angle that the apparent plane of the sun revolves around the Earth. The gnomon allows astronomers to determine the length of the day and the year, noontime, and the meridian, the cardinal points, the length of the seasons, the solstices and equinoxes. The gnomon shadow turns around during any given day, varying in length as it turns. And the length means the angle between the solar ray and the vertical of the pole of the gnomon. It goes to a minimum at the meridian direction. Every day, the same direction, even with the minimum changes. So there is a well-defined direction on the ground. And also the noon time from sunrise to sunset, from the middle of the noon time. Further, the shadow minimum length varies through the year, with times when shortest and some closer to vertical at summer solstice, and times when longest at winter solstice, about 6 months later. Extreme directions at summer and sunrise occur at the solstice, angular rain swept at summer over 180 degrees, and so on. Many simple things can be understood, with the heliocentric picture. When you look at the, I hope it works. Well, okay.
Let me try.
I abandon.
Yes, you push here on the other way.
Yeah, okay. I don't even have a cell phone. I'm not the new inhabitants of this planet. I don't know it. Okay, that is much simpler. Just looking at this graph, you can see that there is one direction, which is the axis north-south. Any point like this, and this latitude, the vertical, the zenith, and then the perpendicular to the plane that the planet follows. So the heliocentric life picture allows to understand things much simpler. But all people did it and tried to get results. And actually they measure all kinds of things. And for instance, you can see here that there is a set of latitudes 23.4 from the North Pole, and also from the South Pole over there in the winter, where you could have in some time of the year the sun at midnight. And in some well, center around the equator, in the Tropic of Capricorn in Cancer, you could have the sun sometime on the vertical, not here, and not in Madrid, certainly. Okay, let me move ahead. So the normal allows students to determine the latitude of the point of observation is given by half the sum of the solar distances to the vertical at both solstices, and half the difference would give the ecliptic inclination. Well, I won't repeat all the things I've written down. I stop a moment, but I want to say something I think is very important in science. I know there is something called big data. I prefer orders of magnitude points, and I have seen theses in which something was studied that you could see that it was an order of magnitude absurd that it would have any effect. And the reason why we can understand these simple things is because the difference between the day and the year is 2.5 orders of magnitude. 360 or 316 is square root of 10 is 3.16 is more important than pi. So the point is that the difference allows people with this complicated picture, I think it's very complicated, to follow things and to clarify results in observations. Well, the normal also could allow observing the moon, because it was something easy to see during the night in some latitudes. And well, they could find out that the moon went, had the inclination of the orbital plane had about 5 degrees to the ecliptic. So sometimes was, let's say, in the winter when the sun is low, the moon, the full moon in the night is up, and the other way around in the solstices when the sun is high during the day, during the night, the full moon, the time of the full moon is low. So they could find out about the crossing of the nodes and so on. And well, also the question of the seasons. They could find out it took more time in going from the vernal equinox through the summer solstice to the autumn equinox. I forgot the word right now. Then going the other way from, let's say, from the fall to the spring. So they found out that probably the explanation with the circle was that the sun was eccentric. The earth was eccentric. And this is close to the idea of later in the 16th century, well, about 16th, 17th century, about the having ellipse in the sun, in that case, eccentric. So in some way, they could find out the eccentricity, in the sense because they could find out there are more days in going from the 22 of March, 22, 23 of 20 or 21 of March to 22, 23 of September, than in going to from the fall to the summer. And this is why in the winter we are closest to the sun. And this is a little strange sometimes for the students, but then it's colder. Well, it is colder because of the inclination. The difference inclination is very high, the order of 30%. The difference of the distances, the centricity of the Earth is a few percent, less than a few percent. So the main point is the inclination. So the students could catch also this idea from the seasons. And now coming to the measurements of space, I try to be short. Aristarchus of Samos, let's say about 250 years before Christ, was the first author. There have been discussions, 18th century before Copernicus, a classical 13th century BC work, now observing and related to the idea of Copernicus, or the center of the sun is at the center of the universe, observations involving 4 ratios for the lunar and solar distance to Earth and radius of the Earth itself. The simplest thing is observing with the simplest optical device, quite clearly in the graph, the angular size of the moon, which is half a degree. He gave 2 degrees, and Archimedes couldn't understand it because it was almost contemporary, because he knew that it was half a degree. It was well known to the Greeks in the 3rd century. Maybe this was a young kind of early youth kind of work. The solar eclipse also proves that the angular width of the sun is about the same. So at the end you have the line over here, which is a very curious ratio. Well, observing the sun is a little more complicated, and I'll say a little more about this later. And he observed the half-moon condition when the angle sun-moon-earth is 90 degrees. He could find out, he could measure the angle from the Earth to the Moon and to the Sun, and found the ratio of the distance to the Moon and the Sun. Roughly, it is about 18 times too high, because the distance to the Moon changes somehow, because the eccentricity of the Moon is substantial, let's say. And the actual value is quite different. So things he found out from these results had a lot of mistakes from the observation, which were very hard to carry out. And finally, in lunar eclipses, the shadow cone of the Moon is about 2.7 times, and he measured about 2 times. So lunar eclipses are easier to accompany away from the Sun, so the Sun does not disturb the sight, and also more often observable. So he could find out let's say the ratio between if he knew the radius of the Earth, he could find out from these equations that I will not stop to explain because they are trivial. They could find out all, with the other previous measurements, all the sizes and distance to the Moon, the Earth, and the Sun from the Earth. About 1/3 century after Aristarchus, still in the maybe 220 before Christ, I don't remember, Eratosthenes estimated R sub e, the rise of the Earth, from first distance from some agrimensors from Egypt with important, let's say, property or commercial rights, from Alexandria to Aswan, it's an old town in the northern tropic, supposedly in the same meridian. This is wrong, but not too much wrong, in using a gnomon, the solar distance to the vertical at Alexandria. So they have the arc, an arc at the distance, and the arc and angles, so he could find out the radius. The end result, observations were poor, all of them. 2.7 times, we gave 2. So decided, but still, besides, I think most of the people think that he was the first to propose the idea that the sun is the center of the well, whatever. He measured things, he made the measurements. He made mistakes. In some cases absurd, like 2 degrees for the angular width of the Moon and the Sun, which is about 4 times less. In any case, Aristarchus de Samos is probably some very important people to care about in history. Okay, thanks.
Thank you, Ron. Questions, Ron? No? Okay, so thank you again. So this concludes our session. So thanks to the speakers, and thanks to the computers for cooperating, and thanks for the support.